Okay, a lot of words here. If we look at the end, oops, I think I might have cut it off. Oh, find the lower bound of the 99% confidence interval for the difference in population mean weights between baseball players and hockey players. That's our goal, right? We want a confidence interval, and it's an interval for the difference between two groups, okay? For the difference in the mean of the two groups. So we have a formula for that. If you get two different means, so we'll call one x bar sub 1 and x bar sub 2, and you want to construct a confidence interval for the difference, this is a good way to compare those two means to see whether they're different enough from each other to say, hey, this isn't random chance, there's something fundamentally different about these two data sets. And so here's the formula. We multiply it by a z star, which is just really to highlight that it's a z-score that helps us find a central area, right? So if you want 90% confidence, you don't want a left-tailed z-score. You want 90% confidence in between here, okay? So they give it to us, luckily, in this table, so we don't have to go look at a table. That's our z. We're going to grab that from the table in just a second. You multiply that by the square root of the sample variance of group 1 squared, divided by the sample size of group 1, plus the sample variance of group 2 squared, divided by the sample size of group 2. This is the formula for the confidence interval two means. Now that we get the formula, now we can just plug things in. We got 48 in one group, so that's n sub 1. That's the sample size of one group. And they got a mean of 195 pounds. So in here, n sub 1 was 48, and the mean was 195 pounds. So we're going to plug that in here for x sub 1. Ran a sample of 54 professional hockey players, so we got a different group, different sample. That's our n sub 2 is 54. It's the sample size of the second group. And it's got a mean weight of 210, so x bar sub 2 is 210. Population standard deviations baseball is 32 and 28.5. So actually they gave us the population standard deviations. The only difference is that you would use this for notation, sigma. Okay. So we've got 32 for one of the population standard deviations. And then we got 28.5 for the other standard deviation. So final part here is that it's a 99% confidence interval, so 2.576 is what goes in here for z. And now we got something to crunch out in our calculator. Okay. Once we do this, when we do the minus part, that gets us our lower bound. Okay, so I can pull up the calculator on the screen and show you what I do. I'm going to figure out each of these fractions as a decimal. I'm going to do 32 squared and then divide by 48, so that's 21.3 repeating. I forgot it already. 21.3 repeating. And then the other one is 28.5 squared. So that's 15.0042. And then our z-score out here is 2.576. And I guess we can do this right now too. 195 subtracted by 210. That's negative 15. Okay. And then we can simplify the square root now. So we get 21.3 repeating plus 15.042. And then we want to square root that result. And then while we're at it, we just found out that this is 6.03. So while we have that in our calculator, let's multiply that by 2.576. So we got our margin of error finally. It's negative 15 for the difference in the means, and it's 15.536 for the margin of error. The lower bound is the lower result, right? So take negative 15 and subtract it by 15.536. So negative 15 subtracted by 15.536. So negative 30.5, and it says round to the two decimal places, so I'm going to say negative 30.54 is my lower bound. And I guess I don't have to calculate the upper bound, but just in case. Negative 15 plus 15.536. So we got 0.54 to the second decimal place. That's our upper bound. Okay, and then an important thing to note when interpreting this confidence interval is it's just barely in there, but 0 is between those two numbers. So that means it could be that these two means are exactly equal to each other. There's not a statistically significant difference because 0 is still possible.